All right, so you've submitted the project. I hope that was a big relief. I don't see anybody who looks like they were up all night working on it at the last minute. So that means that you've learned from your earlier recklessness, and you're being more measured and professional now, getting things done early, not doing all-nighters. I've been reading a book about sleep, and it's just really shocking, the deterioration of both like your physical abilities, but also your mental acuity when you stay up all night. And just like even if you only get 6 hours of sleep instead of the usual 8, it totally wrecks you to the point that you might as well come to class drunk if you're just going to pull an all-nighter. So get your rest and have a beer before class, and it'll be about even, I guess is what I'm saying. Let's take a look at some announcements here. We're getting pretty close to the end of the semester. This is one of only 3 lectures that we're going to have together as a class before the semester is over, because class on Thursday is online. I'm going to be going down to Clemson again to work on the FE exam, so that lecture will be posted on YouTube. I'll give you the link to it when it's ready, and then we'll have 2 live meetings next week, but then that's it. So the homework that's having to do with the direct step method, which was last time, and the standard step method, which is this time, that assignment's due on Thursday. So relatively quick turnaround for that assignment. But the good news is we're going to work 2 examples in class today that I think will help to make the corresponding standard step problem in the homework pretty simple and straightforward. So as far as grading your projects go, it's probably going to be next week before I'm able to finalize that, simply because I'm also going through the engineering cost analysis projects at the same time. And I want to really be thorough and give your work the time that it deserves, because I know everybody's put in a lot of effort, and I don't want to just breeze through that without really looking and understanding what you've done. So I'm going to grade it as quickly as I'm able, but it won't be this afternoon, is my point. All right, any questions related to the announcements before we start talking about the standard step method? Well, let's just begin with a review of why we need the standard step method and what we talked about last time. You know, this is the section of the course where we're talking about gradually varying flow. Here is a backwater curve, as it's called. And so what it means is that there's some obstacle that's interrupting the flow. And ordinarily, if there's no disruptions and if we have steady conditions, the water will set up and flow at its normal depth, meaning that we have steady, uniform conditions. And so then the depth that you'd calculate would just be based on Manning's equation. But anytime you have a change in the flow rate over time, meaning unsteady conditions, or some sort of a hydraulic feature like a weir, or a change in slopes that are meeting together, flow over a drop-off, any kind of a disturbance that's going to set up non-uniform flow, then you have to ask yourself, is there going to be a hydraulic jump? In which case we use the Bellinger momentum equation to calculate the sequent depth coming out of that hydraulic jump. Or if it's a gradual variation, then we have a couple of different tools to allow us to calculate how long is this backwater curve. In other words, how far upstream of the obstruction do you have to go until things are back to normal? And so these are real-world questions. Whenever someone is filling in a creek, you know, to get maybe a bigger backyard, or when they're choking down a creek to put in a culvert underneath a roadway, any change like that is going to be non-uniform flow, and it causes a disturbance upstream. And so we have to ask, you know, is it going to be causing the water levels to rise so much upstream that now other property owners are somehow threatened? So it's a really relevant question. And what we did in the direct step method was we divided this section of gradually varying flow into pieces. And in this example, the number of pieces that we used was just based on what was the total elevation difference. Because we knew a measured depth immediately upstream of the obstruction, that was a given. And then we could calculate, based on the slope of the channel, the roughness, the flow rate, we can calculate with Manning's equation what's going to be the depth when it finally does match back into normal uniform flow. So we knew kind of like the beginning and the end of that curve, but we don't know how long it is. And so we said, well, we want there to be maybe a maximum of 0.5 meter of elevation change for each of these steps. So then that told us how many segments to divide the section into. And just we roughly evenly said we'll just have it come down every, like a certain amount until finally it matches up at the uniform flow. The question is, how long is each of those segments? That's really what we're trying to do with the direct step method, is calculate the length from a measured known depth up to a depth that we know is going to occur eventually, whether it's the uniform or just some arbitrary depth. I think in this example it was 3.8 immediately upstream of the obstruction. We could have said, how far upstream do you have to go until the depth is 2.5? And so then we could have just divided our backwater curve into as many steps as it takes it to get to that depth. All right, so any questions so far on the setup of the scenario or what we're trying to accomplish in this analysis? I think it's really important to just take a step back and ask, why are we jumping into this intricate method? What's it all about? And the what's it all about is how long is that curve? So the process then, what we did was we said for each of these sections, we have some assumed depth. We don't know how far upstream it is, but we know that somewhere there's going to be a location where the depth is 3.2. And if we go further upstream, because it's getting shallower, there's going to be another location where the depth is 2.7, and so on and so forth. So we have these spots with some known depth, and what we're saying is, well, let's calculate the difference in specific energy in that segment. So from the segment here where the depth is 3.8 to the segment where the depth is something else, how much specific energy is lost? And remember, specific energy is just the depth and the velocity head. So in this direct step method, we're ignoring the delta z when we calculate the specific energy. And we also calculate S sub f, the slope of the energy grade line, using Manning's equation. So then we calculate the difference in E, the average S sub f, and then we use this formula to calculate the segment length. And so the spreadsheet that I demonstrated in class on Thursday last week was just all following through this process so that we could say what is the segment length for each of these pieces, and then we added it up all together. And I think I went a little bit over time last time. We were rushed through that example, and I intend to give you back those minutes today. But the question was, how far is each of those segments, and then the cumulative backwater length is the sum of the segments. So the problem with the direct step method, it's nice. It's got some great advantages. It's pretty simple to apply, honestly. But the biggest challenge in applying this direct step method in the real world is that it's really not easily applied to situations where the width of the channel is changing, or especially if the shape of the channel is changing. It assumes a constant prismatic channel width. And so it's great for rectangular channels, or it's great for a trapezoidal channel that is staying the same width and it's not transforming its shape. But any kind of a natural channel is pretty unlikely to follow those limitations. And so, if we want to calculate the depth upstream in a river, where maybe a river is constantly changing its width, we need a more robust method. And that's what the standard step method does. It overcomes this weakness of the direct step approach, and it allows us to calculate the depths regardless of the cross-sectional shape. Okay, so this alarm means that we're having a pretty significant shift in some of the terminology and how we've used it so far. So in the past, the number 1 always meant upstream and 2 meant downstream. That's what we use in the energy equation, in the direct step method. The lower the number meant it's further upstream. But here in the standard step method, the nomenclature is a little bit different. 1 is what we're going to use to mean the location where we know the depth, and 2 just means the place where we don't know the depth. And so it's not always an upstream-downstream situation, because when we're applying the standard step method, whether you work upstream or work downstream depends on the flow regime. If you have subcritical conditions, then the convention is to start with a known depth downstream and then work your way upstream if you have subcritical flow. So the example that we worked last time, that was subcritical flow. We were working upstream, and we'd do the same if we were applying the standard step method. But here's where it gets tricky, is if you have supercritical conditions, then your known depth would be some upstream location, and then you're working downstream towards the unknown depth. And so in that case, 1 would be upstream, and 2 would be downstream. So in our illustration today, I think we've got one example where we have subcritical flow, and I hope at least this other example is supercritical. We'll take a look and just to make sure. So the method is to do a total energy balance, not a specific energy balance like we did in the direct step method. Direct step method was a specific energy balance. Here we're doing a total energy balance. And so you'll notice from the diagram, we're back to measuring Z. So Z is the elevation from some datum up to the bottom of the channel. And then what we're calling water surface, WS, that's the combined distance from the datum to the channel bottom, and then from the channel bottom to the water surface. And so in other words, WS, water surface, is Y plus Z. I'm going to leave that on the whiteboard as a reference because we'll want to remind ourselves of that a little bit later. Okay, so if we just consider all of the energy at 1 and all of the energy at 2, if we just look at what is the total balance on energy, so at 1, there's the water surface, meaning the depth and the elevation. Then we go up the velocity head at 1, and that takes us to the energy grade line, also abbreviated here as the total energy line. And then the head loss, H sub L. It's very strange for us to see the head loss term on the left side of the equation instead of on the right side of the equation, but just remember that here, this was a subcritical illustration, and so 1 was the downstream location. And when we've done the energy equation in the past, the head loss term has always been lumped in with the downstream terms, because what it says is that the energy upstream is equal to the energy downstream plus the losses that have occurred due to resistance at the bottom of the channel. Okay, so we're just accounting for these losses. That's the question, is how much loss has there been as the channel is not only, the water is flowing downstream, but now the channel is changing its shape as well. So here's the procedure that's summarized in the template file I've given you. That spreadsheet template file says, let's begin with some assumption for the water surface elevation at 2. Because 2 is the location, remember, where we don't know things. But you'll already be given all of the information at 1. So at 1, you're going to know the flow rate, you're going to know the depth, you'll know the delta Z. So everything is already defined at this known location. And you remember, number 1 means known. So at number 2, we're going to have to solve this iteratively. We're back to the tools we've used in the past where we start with some guess and then we check our guess to see if it holds up. It's not a direct calculation like the direct step method was. Here, we're going to have to guess what might be the depth of the water at location 2, and then we're going to go through this process of checking our guess and then correcting it if it wasn't exactly right. Okay, so we'll just assume how deep the water is, because we don't exactly know when we're combining the two things together. What makes it uncertain is the fact that, remember, the channel is changing its shape at the same time as we have non-uniform flow. So that's why there's more uncertainty there than there was in class on Thursday when we were doing the direct step method. Is in the direct step method, we didn't have two things changing simultaneously. Here we do. We've got the water surface coming back into equilibrium at the same time that the channel shape is changing. And so we have to just guess at 2 what's the depth. And by the way, you can look at the water surface profile at 1 to know whether it's getting deeper or shallower upstream. Remember those profiles like M1, M2, M3? Those will always give you a clue of whether the water is going to be deeper or shallower as you work in the direction of the unknown. Okay, so based on this assumption of how deep is the water at 2, we're going to calculate the observed head loss, just in the difference in energy. And here E means the total energy. It's not the specific energy. Find the head loss in the total energy. We'll calculate the head loss on the basis of the slope of the energy grade line at the midpoint. So again, we're going to use that trick of finding out what is the slope of the energy grade line in the middle between these two sections. And here, this C value is related to the fact that because you've got a change in shape, you may remember that when we did like channels getting wider or channels getting narrower, there was an energy loss coefficient, a C value, associated with that transition. So here, the C value that's having to deal with the difference in velocity head is the same C value that you'd use in a transition for a channel getting narrower or wider. It's kind of like a local loss, in other words. So the total head losses are related to the friction losses over the length of the segment, and then the local losses / channel geometry change effect in this second term. And then what we have to do is compare whether the observed head loss and the calculated head loss are equal. And if they're not, and they most certainly won't be, at least initially, because remember, this is just all based on a guess. So if our guess wasn't right, then we can estimate a calculated water surface depth, and then we average our initial depth, so the previously assumed, or if we're doing this through many different iterations, the water surface elevation in the previous step. So the updated is just an average of this newly calculated depth and the previous depth. And so what we use to come up with this updated depth is looking at the energy at 1, meaning the water surface, the velocity head, and the energy loss. Remember, 1 is downstream, and then the energy at 2. So again, we're just looking to see if we can correct how much of a difference in energy there is. And so you're saying, what water depth would it take to get these two head losses to match up? You know, if the head losses aren't equal, then that means our guess must have been wrong. So we're applying a correction factor when we calculate a new water surface elevation for this calculated location up at 2. All right, so that's pretty abstract, but that is an outline of what our workflow process is going to be. And you just keep going over and over until the observed and calculated head losses are equal. And once they've converged to within, 2% or so, just our standard numerical convergence criteria of a couple percent, then we can finally quit. All right, this is the example that we're going to use to get a feel for the process the first time around. You'll note, first of all, that we're working in traditional units. And so Manning's equation is a little bit different when you're working in traditional units. It has that 1.49 factor in front of it to get the units to work out in Manning's equation. So I think that's in the template file that I've supplied you with. Section 1 is where we know the water depth. Section 2 is where we're trying to find out what is the water depth here at Section 2. We're not exactly sure what the depth is, but we do know that it's 1,000 feet upstream. So 1,000 feet upstream, it's going through this transition. You'll notice that it's 25 feet on the bottom width of the trapezoidal section. So over the course of 1,000 feet, what it's doing is those sides are coming up and they're becoming vertical. And so the flow used to be not only in this center segment, but also in the sides of the trapezoid. Now the water is going to be confined just to this vertical section. And so it was 5 feet, and we're wondering how deep it's going to be. Now, the slope of the channel is defined by the fact that it's 1,000 feet, and you'll notice that the invert is 2 feet higher at the upstream section, because the invert here, meaning the bottom of the channel was 5 feet above the datum, and so Z1 is 5 feet, Z2 is 7 feet. So we could get the slope of the channel from that, the roughness of whatever this material is, that's given to us. The flow rate is 1,000 cubic feet per second, and then that C factor that's having to do with the expansion contraction coefficient is 0.3. Okay, so I see many of you have computers, not everyone. If you don't have a computer, you could scoot up next to somebody who does, or if you just want to observe, then that's okay too. Here is our first example. So in the template file, I've already identified a spot where we can key in the flow rate that we've got. So that's 1,000 CFS. The end value, the Manning's roughness of that channel is 0.05. Okay, the Z1, the elevation above the datum to the bottom of the channel at section 1 is 5 feet. It's 7 feet at section 2. The expansion/contraction coefficient is 0.3, which just means that 30% of the velocity head is lost over the course of that transition. And then the length between the section is 1,000 feet. Okay. What direction are we working here? Are we working upstream or downstream? I guess we haven't conclusively determined yet whether conditions are supercritical or subcritical, and we can do that. But which way is the water flowing? I guess the cat's already out of the bag. They've already told us that section 1 is downstream and section 2 is upstream. So the problem statement itself tells you it's subcritical. But the point I want to make is, even though our calculation is going from downstream towards upstream, keep in mind that the water is actually flowing from the part where it's a rectangular channel, and the water is encountering some channel that is tapering to become trapezoidal. And so, although we're calculating in the different direction of the water flow, just keep in mind that the water is experiencing an expansion. And so the C value is an expansion coefficient, because that's what's happening, is the channel width is expanding. Okay, so we know the initial depth of the water is 5 feet. That's a given. The water surface depth at section, oh wait, hold on a minute. Your template file is a little bit different than mine. Let's add a column. I think it'll just make our calculations a little bit simpler. Right-click on B, and let's call that WS1 in feet. Yeah, I think that'll make the calculations a little bit simpler, and you'll see why in just a moment. And just because I'm, all right, you don't have to make that subscript. That's maybe over the top. Okay, so the water surface is the depth, Z1, so I'm going to anchor that reference to Z1, plus the depth. Remember, WS is depth and elevation. Okay, so 10. The cross-sectional area, here where we know the condition, so it's trapezoidal. And so the area is 5 by 25, so I'm going to have the channel width of 25 times the depth of 5, and then the side areas. And so we've got, let's see, if it's 2-to-1 side slopes, that means it's 10 feet on either side and 5 feet deep. So I'll just draw that on the whiteboard so there's no question about this trapezoidal geometry. Okay, so we've got 5 feet deep and 25, so this segment here is 5 times 25, and then these two side segments, if it is a 1 to 2, then that means this is 10 feet on either side. Here's 10 feet as well. And so together it's 5 by 10. The two triangles together are a rectangle that's 10 by 5, right? So 25 times the depth plus 5 times 10. 175 square feet is the cross-sectional area at this known location. Okay, velocity is just going to be Q divided by the area. And I guess since I'm going to drag that down later, I need to be sure to anchor any reference up there to these constants. All right. Wetted perimeter. So the wetted perimeter is going to be the 25 meters on the bottom. So the wetted perimeter is 25 feet here, and then the square root of 10 squared plus 5 squared, and there's 2 of those. We don't always have to go to table 10.1. We can just do it the old-fashioned way from time to time. So 25 feet plus 2 times the square root of 5 squared plus 10 squared. Yeah, 47.36. So that's our wetted perimeter. The definition of hydraulic radius is area divided by wetted perimeter. Okay, and then the energy is going to be, total energy is the water surface plus the velocity head. So total energy is y plus z plus v squared divided by 2g. So the total energy is those 3 terms: depth, elevation above the datum, and velocity head. So depth, well, I'll just do water surface plus the velocity head. V squared divided by 2 divided by g. Caution, warning, 32.2, since we're in traditional. All right. So that's our total energy at 1, and now the slope of the energy grade line, we're going to use Manning's equation for that. Okay, so equals N times Q divided by 1.49 divided by the area divided by the hydraulic radius to the power of 0.66667, and then all of that is squared. Okay, I'm going to pause for a moment and circulate around to see if we are all on the same page here with the calculations, see if there's... Okay, so at 1, it's going to always be these conditions. This is a location where we've measured and we know what the depth is. And so we don't have to do like lots of iterative guesses of what's going on at 1, since it's the known section. So what I'm going to do is highlight all of those values and just drag it down. Now, how many? You can see that just by virtue of the formatting how many I think it's going to take. You don't know when you're just getting started. Oh, it looks like it's counting somehow. Okay, if we just do 5 there. Okay. Sometimes Excel starts to count rather than use the same data. All right, let's see. See, it's counting. So I'll just do 5, 5, 5, 5, 5. The depth stays 5 there. Everything's going to be the same. But we just need to have row by row it available to look up these values. Okay. So at location 2, we just have to start with some initial guess of what the depth is. And we have subcritical flow in this example. and it's going to be deeper at section 2. Let's just say 5.1 as a starting guess. 5.1 feet. All right, so if that is our guess of the depth at 2, then the water surface, remember the definition of water surface is depth and z. So it is this depth plus z2, and I'm going to anchor that reference because I'll be dragging it down. Okay, cross-sectional area. Thankfully, this is rectangular, so the geometry is a little bit easier on section 2. The area is just the 25 feet bottom width, 25 times the depth of flow. All right, the velocity head at 2. Oh no, this isn't the velocity head, this is just the velocity. So the velocity is the Q divided by A at that location. A wetted perimeter will be twice the depth because it'll be on either side. The water is in contact with the channel on both of the sides and the bottom. So for a rectangular channel, it is 25, which is the bottom width, plus 2 times the depth. That's the wetted perimeter. Okay. Hydraulic radius is area divided by wetted perimeter. Total energy at 2 is going to include the depth, the elevation above the datum, and the velocity head. So remember that water surface is y plus z. So for E2, I'm just going to say it is water surface at 2 plus the velocity squared divided by 2 divided by 32.2. So we've got E2. Now the slope of the energy grade line, again we're doing the same thing using Manning's equation to find out what's the slope of the energy grade line if this is the depth. You know, for a depth that's that and for a certain flow rate that's going through the channel, what would be the slope of the energy grade line in that situation? When you have non-uniform flow, Manning's equation won't tell you the depth at a certain location, but it will tell you the slope of the energy grade line at that instant when the depth is some known value. Okay, so the slope of the energy grade line, so we're doing this formula again. N, anchor the reference, times Q, anchor the reference, divided by 1.49. Technically it's 1.486. But most references round it off to 1.49. But just in case it ever comes up in Final Jeopardy, it's 1.486, all right? 1.49 divided by the area divided by the hydraulic radius to the power of 0.66667. All right, and then all of that is squared. Okay. So we've got slope of the energy grade line if the depth happens to be 5.1 feet. All right, so if the depth is that, if it is that depth at section 2, then what would be the observed head loss between the 2 points? And so observed head loss, what we're saying is if we just look at the E2 versus the E1. So head loss observed, it seems distorted. E2, so equals E2 minus E1. The water is flowing here from 2 towards 1 because it's going from upstream to downstream. So we're losing 2.548 feet of head loss if the depth is 5.1. Like where is that energy being lost? Well, it looks like it's mostly being lost in the fact that, let's see. Why is the E so much higher? Oh, it's the elevation. It's mostly the elevation change, the 2-foot elevation change, right? I mean, the 0.548 feet of head loss. The rest of the head loss is due to the fact that the, I guess, the channel changing shape. Okay, now S sub F bar is just saying the average of the two energy grade lines. So I guess I don't have a formula on the page for that one. It's just the average of these two. Okay. So it is at 1 and at 2 divided by 2. Pause for a moment just to see if we're all still working on the same page. Okay, so on this first row, just to reassess where we're at, what this is saying is, let's assume that the depth at location 2, which is the upstream spot, upstream where it was rectangular, the depth was 5.1, and then when it went through that transition, we know the measured depth is 5 feet down at section 1. So what we're going to find is that this depth is too shallow. We're going to see that in just a minute. But all of these calculations are just saying, okay, so if it was 5.1 feet of depth upstream at 2, well then what does that mean about the slope of the energy grade line? How much energy would be lost? It's like this cascade of calculations and assumptions that are based on what if the depth was that. And so we saw that for that depth of 5.1, then that would mean an observed head loss of 5.48 feet. But the calculated head loss, well, the way that we're going to get the calculated head loss is with this formula. And so it's with the slope of the energy grade line, average over that section. Okay, so this is our S sub F bar, times the length. It's 1,000 feet distance between the two. And then we add plus the C value, which is our expansion coefficient, times the difference in velocity head. Now this is where I wish I had a separate column that was just the velocity head. That would be a little bit simpler. But all right, so C times the absolute value, because that's what these vertical lines mean, absolute value of V2 squared divided by 2 divided by 32.2, because that's G, minus V1 squared divided by 2 divided by 32.2. Okay. So the calculated head loss would be 9.578 feet. And these two should be matching. If we've converged, they should be matching, and they're not matching. So that means our guess wasn't right. So what we want to do now is we want to come up with an updated guess. So this calculated water surface at 2, remember our first water surface at 2, this was assumed. This WS2 was based on an assumption. Our calculated is going to be the water surface at 1, so we can scroll over here to the left and get water surface at 1, plus the velocity head at 1. Okay, velocity head at 1 is velocity head, so velocity to the power of 2 squared, okay, squared divided by 2 divided by 32.2. Water surface 1, velocity head at 1, plus the calculated head loss that we just, it's in cell U30. Since I'm centering it, I can't quite click there, I don't think, so I have to type that in, U30. Okay, so that's the calculated head loss, and then minus the velocity head at 2. So minus velocity squared divided by 2 divided by 32.2. This is the calculated water surface at 2. And then the updated is going to be just for us to take an average of our previous value and this new value. Now our previous value for the water surface at 2 was 12.1. Our new updated improved version of that depth, 19.13. So we add them together and divide by 2. We can't just use this directly because it would overshoot. So we kind of just have to only apply half the correction each time for it to eventually converge. Otherwise it won't be numerically stable and it won't converge. So percent difference is just a relative indicator that we can use to know whether it's improved. And so for percent difference, maybe we would have the updated minus the original divided by updated times 100. So it's the change divided by this value that we assume to be correct times 100. So 22.5% difference. So our increase, this updated value is 22.5% larger than the original starting value. And what we're going to aim for is, let's just see how low we can get it. 1% generally means, we're good enough. But in this case, all we have to do is just drag things down, with the exception of this next cell. So our initially assumed depth, we're not just going to guess 5.1 now. What we're going to do is we're going to find out what would be the y based on this updated water surface. Okay, so water surface is y plus z. So how do I calculate the y if this is the water surface elevation? Equals water surface minus the z. And z2 is 7 feet. Okay, I'm going to anchor that reference to z2. Okay, so the new guess of the depth is our updated water surface minus the elevation. Okay, so 8.62. Now I think if we've anchored everything correctly, I think we can just highlight all of these and drag down a notch, and let's just see what happens. If I forgot an anchoring somewhere, it's going to be pretty obvious. But I think it's operating the way that it should, actually. So we have our new depth that's assumed at 2. And did we get closer together on our guess of observed and calculated head loss? Yep, it got a lot closer. If you look at our updated and our initial guess of water surface, it's pretty close. Well, that's not right. Yeah, let's put in the flow depth there. All right. That's better. Okay. So we're getting closer, right? If you look at the percent difference, we were 22% off the first time around. Now we're 2.6% off this time. Now I don't think we even have to manually type in this initial guess anymore. We can just select everything and drag it down a couple of rows and see where we're at. We're already under 1%. But since it's just a flick of the wrist to go all the way down, let's do it and see where things finally converge. If the depth is no longer changing, to the degree, I'm going to be measuring depth to the 100th of a foot. And so once it's telling me 8.05, 8.05, 8.05, then there's no sense of, even if the observed and calculated head loss is still changing ever so slightly. 0% difference. Okay, so the answer is, if we just want to draw a conclusion here, the flow depth at the upstream location, that is to say where the section is rectangular, is 8.05 feet deep. That is our conclusion. So let's just review what we did. Like, what was our process? We did a comparison of energy. And what we're saying is there's two ways of looking at the energy. You can look at the energy based on what is the delta z, what is the change in depth, what is the velocity head difference. That's what we were calling here the observed head loss difference. And then the calculated head loss is based on the slope of the energy grade line. And the slope of the energy grade line is calculated based on Manning's equation. And Manning's equation just says for a certain roughness and a certain flow rate, there's going to be a slope of the energy grade line. And if you apply that over some length, then that tells you how much energy loss there was on a calculated basis. So we want those two to match up. We want our observed and calculated head loss to be in equilibrium. And if we do that, then we know that we have the correct depth. Now, I got a similar question. I assume someone out there is wondering, well, couldn't we just do goal-seek the first time around? Who is wondering that? Yeah, I'm not sure. I've never tried, so why don't you try it and get back to me? I'm not sure if it would work, though, because remember, what we're having to do in the updated water surface elevation is take an average of the two. So I don't know if that would work or not. My guess is probably not, but I've been wrong before, and I'm sure I'll be wrong again, so who knows. But let's take a look at a supercritical example. At least I think this one is supercritical. No, it looks like this one's subcritical as well. We've got triangular going to a half circle downstream. We know that they're 100 meters apart, the roughness 0.045, and we're putting 1.5 cubic meters per second through there. So, I've already calculated the critical depth and the normal depth. All right, that confirms it. That this is subcritical conditions, because if the critical depth is 0.65 and the normal depth is 0.98, then that means we've got a mild slope. And here at location 1, the depth is 1.5. So the question is, what is going to be the depth here where it goes to triangular? So in the template file that I've provided you, we've got basically the same setup, but note here that it's cubic meters per second, z is in meters, length is in meters, and so when you do the g, then be sure that you use 9.81 this time. And just to make things a little bit simpler, let's add that water surface column in again. It was next to the y1, between the y and the a, so if we add a column here in B, we'll call that the water surface at 1. And heck, while we're adding things, we might as well even add a velocity head term, because we'll use that later. So, no, let's not. What would we even call it? All right. So at 1, where we know the conditions, we know the depth, we know the elevation of the channel bottom, so the datum is right at the bottom of the channel there at 1. I'm going to pause and let you work through this one independently without me narrating and interrupting you, but I'll be circulating around with the solution to see if you're on the right track, and then when we've maybe got 5 minutes left, I'll start doing the solution on the screen so you can double check to see if you got it. if you haven't already started with something else, try a depth of 1.5. Just choose the same depth at that upstream location and see what are all the calculations that arise from that for our triangular. All right, so the answer to this second one is that the depth should be 1.26 meters. And I think the tricky thing here is maybe the geometry of the of the half circle and of the triangle. But if you figure that out, it's really the same process as it was before, where I added again a column for the water surface at 1 and the water surface at 2, just to simplify the calculations. So we see that the percent difference is rapidly declining and it's eventually converging on 1.26. I'd be glad to email you a copy of this finished spreadsheet just so you have the solution for the second example. I'll do that immediately after class, but I did want to point out one thing. I took a second look at the homework assignments, and actually both of the problems that you have due on Thursday are direct step. So what we're doing today, the standard step method, that actually doesn't come until homework 16. And homework 16 is going to be due on Tuesday of next week. So we still actually do have some time for you to continue to absorb the standard step method. It's just those 2 homework problems that are due on Thursday are both direct step. All right, that's it for today. I'll send you the finished solution of that second example via email. Remember that we don't have class meeting on Thursday, but I will see you a week from today back to our normal schedule in person. So have a good day.